Rosemary Harris. Full screen. There we go. You take that one. Good. Sorry if I just about that. Yeah, Rosemary from UCL, so please.
Thank you very much. It's very nice to be here. I'm a little bit on the fringe of the main topics, but I'm learning a lot and enjoying it. So I'm in maths at UCL, which is somewhere at the back here. And I'm going to talk today about something that doesn't directly relate to either epidemics or energy systems, but does have to do with some ideas about how to model decision making when memory plays an important role. And in the interest of time, I'm only going to talk really about the traps part of the advertised title, but if you're interested in more recent work on interactions, then do ask me afterwards. So by way of background, I'm very much team stochastic, and most of my day-to-day work is in stochastic processes. I've got a background in statistical physics, and I'm particularly interested in characterizing fluctuations, rare events, atypical behavior, particularly through the lens of large deviation theory. And a lot of my work relates to various scenarios where memory plays an important role, or there's some kind of switching dynamics in time. Some of that's quite theoretical, but I'm also interested in applications to various complex systems, including a little bit to behavioral modeling. And that makes sense because, as Kahneman says in his book, there's lots of randomness in the decisions that people make, so these tools from stochastic processes can be useful. And today I'm going to talk about one very simple model of decision making and try and convince you that the interplay of memory and fluctuations can lead to quite different forms of long-time behavior. And I think take this as a cartoon model to illustrate a mechanism rather than a model of any particular situation. So modelling decision making, so I'm from UCL, so it's good to start with Jeremy Bentham. Here he is in his box in our student centre. It's really there, you can go and see him. And he's of course famous for this greatest happiness principle that human beings are supposed to take decisions in a way that maximises their happiness. And this is sort of the forerunner, as I understand, I'm a bit nervous, we've got real economists here, of modern utility theory, where agents take decisions to optimise their utility. And for me, I just think of utility as a measure of satisfaction, of benefit, of reward from a particular decision. How does memory come into that? Well, memory plays a role in how we associate utility to decisions we're going to take. What reward we think we're going to get from particular choices depends, at least to some extent, on what happened last time we made those choices. And the problem there, of course, is that our memory is also not perfect. And how humans remember things is another very complicated story, but one heuristic, again due to Kahneman, is this so-called peak-end rule, famously illustrated in experiments on colonoscopies, I won't go into, but the idea that what dominates our memory in at least some scenarios is that the peak bits, the worst bits or the best bits, and the last bits, the most recent bits. And the question that I'm trying to answer here is, okay, if I take that kind of memory of extremes, I'll concentrate on the peak part, how might that play into future decision making? And we're going to look at that, as I say, in a very simple toy model. So here's my 101 discrete choice model. I've got a single agent repeatedly deciding between two choices. So we're thinking of the kind of decisions that you make many times, whether to take the bus or the car to work, whether to have cornflakes or toast for breakfast. So we've got a single agent repeatedly deciding between two choices, and we keep track of the number of times they make the plus choice and the number of times they make the minus choice. So there's no kind of moral superiority. The plus and minus are just labels. We have the number of plus choices up to time t and the number of minus choices. So this, of course, is just a one-dimensional random walk with some probabilities for going right or left that I haven't yet told you, but are going to somehow depend on past experience. And it turns out to be useful to think about the relative proportion of the choices, which is this kind of velocity variable, so the net position, if you like, divided by time. So if this is 0, it means I've got the same number of plus and minus choices. If it's +1, it means I'm only making the plus choice, only going to the right. If it's -1, it means I'm only making the minus choice going to the left. And in general, to avoid cluttering the slides, I'll drop the time subscript in these random variables. Okay, so that's a kind of random walk. How does the utility, how does the memory come in? So I put it in the model in this very simple way. Every time the agent makes a choice, they get a reward, a utility, which is a random variable, u subscript I, from some known distribution that might in general be different for the plus choices and for the minus choices. And it's independent each time. And the idea is that the agent doesn't remember all their past rewards for the plus choices and all their past rewards for the minus choices. Their head's not big enough. They just remember the best experience they had for the plus choices and the best experience for the minus choices. So these are my hat variables here. I hope you can see the hat. U hat plus is the best experience for the plus choices, and U hat minus is the best experience for the minus choices. And it's those things that then feed into the decision that comes next. And I use here logit decision probabilities, where the capital T is a kind of level of noise in the decision, or what some people at least say is the inverse of a rationality parameter. So if capital T is very big, you're so tired or confused or drunk that P plus and P minus are both essentially a half, and you're making your decision by tossing a coin. On the other hand, if T is small, there's a bias in the direction of wherever you remember the best experience, wherever the biggest maximum is. Okay, so that's the model. So what happens? Well, let's first of all look at the simple case where the right and left distributions are the same. So the two choices have the same distribution of rewards. Notice that that still means that at any particular moment in time, the distributions for the maximum random variables will generally be different because they depend on the number of steps right and left you've made. They depend on the number of times you've sampled that distribution. And then you can ask, well, what happens for long times? Is it the case that the model is symmetric somehow? So do we end up with a distribution that's peaked about 0, roughly the same number of right and left steps? A kind of mixed decision state. Or is it somehow possible that the agent gets trapped because of some early experience and ends up only making one of the choices in the long time limit? Well, the answer, as you might guess, depends on the distribution of the rewards, so the distribution really matters here, and on the level of noise in the decisions. And one way you can see that is with a kind of simplified model which retains some of the features of the full model, in which you approximate the random variable for these maximum experiences right or left by the so-called characteristic largest value, which just says if I've had x plus steps right, what would typically be the largest value I would have seen from that distribution? And similarly for x minus steps left. And you can get that simply from knowing the CDF, the distribution. If you make this approximation, then P plus and P minus are deterministic functions of the number of steps right and left you've had, or of the velocity and time, if you prefer. And then you have a model which falls into a class of what physicists call an elephant random walker model, a random walker that remembers its whole history, or, of course, in the maths literature, a nonlinear polyurn problem. And you can use kind of established techniques to look for fixed points you might end up in the long time limit and check their stability. And if you do that for homogeneous utility distributions, you find that extreme value theory, perhaps this is not a surprise, predicts 3 different classes of behaviour depending on the distribution of utility. If your rewards, your utilities are bounded, a uniform distribution, for example, then if you wait long enough, you'll have seen the maximum for both choices, left and right, and then you'll be back to 50-50 tossing a coin, you're never trapped. On the other hand, if you have a distribution with heavy tails, like a Pareto distribution, for example, then what happens is that at some point, you'll see something way in the tails of one of the distributions, and then you'll be overwhelmingly more likely to make that choice again in the future, and to see something even further in the tail. And eventually you get sucked into only ever making that choice. The interesting case is the case where you have exponential tails, and then there's a kind of phase transition depending on the level of noise in the decision. And to convince you that that works, here's simulation data for the full model. So this is 100 time steps just simulating the model with an exponential distribution of rewards. The green points are for a high level of noise, and if you plot a histogram of the velocities you see, then you find it's centered at 0. So you're sloshing around in some kind of mixed decision state. Whereas the red points are for a low level of noise, and now the histogram looks very different. It's got a sharp peak at -1, only ever going left, and a sharp peak at +1, only ever going right. And you can predict where that transition is. But actually, it doesn't really matter if the distributions are the same. I mean, maybe you go through life thinking that Coke is superior to Pepsi, but nothing really matters, right? What about if you have heterogeneous choices? Then you really have a possibility that some early experience can lead you to you being trapped in a choice which is less good for you on average in the long run. And investigating this was the work of Vangelis, who did a PhD with me at Queen Mary a few years ago. And I'm not going to go into the details here, but what you find here, if you look at the average utility, so this is a plot of average utility averaged over time and ensemble against noise for both the simplified model with this approximation and the full model, you find that you have something with a peak, that there's an optimal level of noise which optimizes your average utility in the long run. And you can do a kind of dynamical landscape approach to characterize different regimes and to predict not only where the crossovers are, but how you saturate as time increases. So you can do some scaling for different times. So these curves are different times. But the main thing to remember is there's some optimal level of noise. So I think I'm at the end of time. I hope I've convinced you that memory and stochasticity can lead to interesting effects that might be important in real life. That you can get this kind of trapping by reinforcement, and in particular that some noise is good for optimal escape. You want to have enough noise to explore, to find out what the best choice is, before you get trapped in something that's not good in the long run. And of course, there are many more things that you can do. Correlated experiences, collective effects, interactions, time-varying noise. And what I'm really interested here are the real-life scenarios where this kind of effect might be important. But let me stop there.